Alright, let's take a look at example 8.8. This is in the Survey and Jewett book. All the examples are good too. Take a look at them, work them. If you want extra problems to work, there's lots of examples in this text. And all the examples in the Fundamentals of Physics book by Halliday and Resnick are also good. Okay, so in this we have some sort of mass with some initial velocity moving to the right, and there's a spring. It's going to stop it and make it come to a rest. And we want to know how far the spring compresses. So what's the compression of the spring? Let's call that our delta x. It's initially not stretched at all, so we could just call it what is this point x2? How much is that compression from what we're calling x is equal to 0, where the spring is unstretched at all? Let's use the conservation energy to do so. We're going to use a spring constant k, mass m, initial velocity v1, and the fact that it comes to a rest. And let's call it x2 in the spring, the compression in the spring required to do this. Okay, so we have some initial kinetic energy, some initial potential energy, and it's all going to turn into potential energy final, kinetic energy final. I just always write out the whole thing. Kinetic energy initial, we do have some. It's got some initial velocity. If it has velocity, it has kinetic energy. We don't have any potential. This is unstretched or uncompressed to start with, so there's no spring potential, and we're not moving through any delta y, so there's no gravitational potential. No work is being done in this part, but we're going to do a part B where we're going to add friction. So, how far does it compress with no friction on a frictionless surface? So now we'll call it frictionless. Forgot to mention. All of the kinetic energy is going to turn into just spring stored energy because it's going to come to a rest, right? Velocity is equal to 0, so the kinetic energy term goes away. We're just going to get a 1/2 mv at 1 squared is equal to some spring term, 1/2 k, and we called it x2 squared. And we can solve for that right there. We're done. Just get rid of our 1/2s. We have x2 squared would be equal to mv squared over k, and we take the square root. Right? Check my math real quick. Yep. So that's how far. With that much energy, it would displace to the right a distance of that. But we get a. What happens if we have friction? We got to do one free body diagram, basically just to realize that the normal force is equal to mg, right? We need that for our definition of friction. That friction is equal to mu times the normal force, or mu times mg. Because after you do Newton's second law, you realize that these are equal. So let's say now there's some friction with some coefficient of friction mu. How far does it go now? It should compress the spring less. Friction is going to be taking energy out of the system, just like the spring did, right? The spring took the energy from the block. It then stored it inside the spring. If you let the block go again from rest while the spring was compressed, it would launch with the same and end up going the same velocity on the frictionless surface. If we add friction, though, it's going to slow down as it gets closer and closer and closer. We have a constant force of friction acting against us, giving us a constant deceleration. So how do we deal with it? Well, we only have to do the Newton's second law and free body diagram in that one direction. And let's just look at the work done by friction. We can still say the potential energy initial plus the kinetic energy initial is equal to the potential energy final plus the kinetic energy final. We're just going to add the plus or minus work term here. And if it's friction, friction will be removed. It removes energy from the initial state. That's how I think of it. So I would say the potential energy initial plus the kinetic energy initial minus the work done by friction is equal to the potential energy final plus the kinetic energy final. Alright, potential energy. Initially, the spring was not compressed. It had nothing to do with how much energy the block had anyways. It could have been compressed, and we would have to put a spring term and on the left-hand side. But we don't have one. We also don't have any change in gravitational potential. So we just have the 1/2 mv initial squared minus the work of friction. What's the work of friction? Well, the definition of work is F times, for a constant force, is F times the change in position or the displacement. We would get a negative mu times the normal force times that distance x. We'll call it x2. We could call this some, we'll call that x, and we'll call this that x2. So it's going to travel some x plus x2. And that's going to equal however much it compresses the spring if it comes to rest again. Kx2 squared. And we have the kinetic energy going to 0 in its final state. So what we end up with now is a quadratic. We have x squared and we have x, right? 1/2 mv initial squared minus mu mg x2 minus mu mg x is equal to 1/2, and x is a value that we would know. They would give us the distance to the spring. What we're concerned with is the compression of the spring. So how much did the spring compress to come to a stop with a frictionless surface? Well, that was the first part. This one is, well, what if we added friction in there? Well, it traveled against the force of friction some distance x2, the amount that the plunger went in, attached to the spring, right? That's our delta x, or from x is equal to 0 to the distance x is equal to x2. And it also traveled that distance all the way to the plunger x, so we'd have to include it also. But that's a constant value. It's not something that we're solving for algebraically. And that all turns into 1/2 kx2 squared. Alright, now we can just set this up like a quadratic equation and solve where, let me go ahead and do it for you. 1/2 x2 squared. Then we would want this term, which if I moved it over here, it'd become positive mu mg x2. And then we have some constant terms. This would become a positive mu mgx and a minus 1/2 mv initial squared. All that equals 0. And this is your C. This right here would be your B, and this right here, oh, I'm missing the K, 1/2 kx squared. Right there would be your A. So look, you have a ax squared plus a bx plus c is equal to 0. Throw that thing in the quadratic equation and you get your answer.